f of x equals negative 2 x plus 1 squared x minus 2 cubed. So we're asked to graph. Again, why are we graphing these functions, or graphing functions in general? In order to understand their model and hopefully apply it in different real-life situations. We're going to look at a real-life situation with polynomial functions when no other function would have worked. No absolute value, no radical, no quadratic, no linear. Nothing else would have worked. Only a polynomial function. In a few minutes we'll look at that. Okay, so we get the table going from the very beginning. And remember, once you fill out the table, then you're done. The only thing that does not fit here is the symmetry. I will not take credit for these tables. I was taught like that. I had a wonderful math professor. I hope he's still alive. He was wonderful. He was a wonderful guy. Yes. So that's the only thing. I could not come up with something better than he did, and I cannot fit the symmetry anywhere. So this is the only thing that does not fit in the table. Once you're done with the table, you can graph the function. So first I have to find a domain. What is a domain? Of course. Remember, this is a polynomial function. There is no restrictions. There is no risk. You're not dividing by x. There is no square root. Nothing bothers us here. We can plug in anything and we will get a y value. Good. Let's continue with the y-intercept. When I plug in 0, let's do this together. 0 plus 1. 1 squared. Done. 0 minus 2. Negative 2 cubed. Careful. Negative. Negative 8 times negative 2. Right. You don't have to do it like that. We just wanted to do it quickly. But you can write f of 0, which is negative 2 times 1 times negative 8, and you get 16. Okay, what is the leading coefficient? The leading coefficient is negative 2. What is the degree? Yes. X squared times x cubed. X squared times x cubed is x to the 5th. So degree is 5. Max possible number of terms. 4. All is 5 minus 1. The degree minus 1. It doesn't mean that the function has to turn 4 times. But it necessarily and clearly means it cannot turn more than 4. It's only that. It's max possible number of turns. I swallowed a word. Sorry. Max possible number of turns. Very good. X-intercepts. How many will you give? 5. 5 x-intercepts. Great job. How do I find the x-intercepts? What do I have to write? Exactly. So this is f of x equals 0, or negative 2 x plus 1 squared x minus 2 cubed equals 0. Of course, you will divide both sides by negative 2, and you will get 5 solutions. I'm ready when you are. Yes, 2 of them are negative 1, and 3 of them are x equals 2. What is the multiplicity for negative 1? 2. Very good. What is the multiplicity for 2? Very good. These have to add up to 5, to the degree. Do they add up to 5? Okay, what does multiplicity 2 always do? It will. Very good. Turn. Excellent. What about multiplicity 3? Yes, it will cross, but it will slowly cross. Very good. Excellent. So negative 1, 0, and 2, 0, and I make my obvious notes. Turn, slow, cross. Finally, I want the end behavior. Since the degree is 5 and the leading coefficient is negative, degree 5 and negative leading coefficient must behave like the linear function. Either this or this. So infinity, negative infinity. Odd degree, negative leading coefficient. Odd degree, negative leading coefficient, from positive to negative. And the last thing I'm going to write is about the symmetry, and I'll say f of negative x for sure does not equal negative f of x, and it does not equal f of x, not symmetric. How do I know? Well, a function that turns at -1 and crosses at 2, it's not symmetric with respect to anything. It's not symmetric with respect to the origin. It's not symmetric with respect to the y-axis. It's not symmetric with respect to the origin. So don't waste your time, but you have to write something because the problem will ask. Okay, so now I'm ready to graph. I don't care about my notes. I only care about the table. And here is what the table is telling me. Let's analyze this. So obviously it starts at infinity. It will come down to -1, 0. It will turn because it turns. It will cross the y-axis somehow. It will come back and slowly cross and go to negative infinity. One more time. From positive infinity at -1, 0 it turns, crosses the y-axis at 0, 16. It comes back, and at 2, 0 very slowly crosses towards negative infinity. That's it. I will plot these points. That's my first step. -1 and 2. I will use a different scale for 16, like 4, 4, 4, 4. And I'll put on the coordinate system exactly what I just said. Coming from positive infinity and turning at -1, 0. Somehow it has to cross. Does it go higher and then cross? See, these functions are smooth, continuous functions. If I twist my wrist to graph them, most probably that's wrong. So it has to be something very smooth. So I think it's going to do this and then come down and cross, but slowly, not like this, but like this. How do I know? There are 3 solutions here. Obviously 1. But you know what I mean. It appears 3 times. I do not know this. We cannot determine that without a calculator in this class. If you want to take calculus, you'll be able to do that by hand. So this is our function. So this is f of x equals -2 x plus 1 squared x minus 2 cubed. Notice that everything was in the table. I didn't care about anything else. I have everything in there. So now let's put in the graphing calculator. So let's see what we have. Where is it? Okay. So -2 parentheses x plus 1 squared and in parentheses x minus 2 cubed. Now I will use the zoom 6 just for a second. I already know that there is no point in looking below the x-axis too much. I don't like the graph because it's too much room to the sides. I don't see the maximum, and I would like to see this better. So I'm going to change the viewing window from -4 to 4 with a scale of 1. And minimum, yeah, maybe -4. But obviously the maximum has to go much higher. I don't know. I'm going to At least 16, of course. So I'm going to put 30, see what happens with a scale of 4. Ah, okay, good. Exactly every step as we expected it to be. Starting from positive, and it turns at negative 1, 0. It crosses at 0, 16. It goes to a maximum, a local maximum, comes down as expected, and very slowly, not very slowly, but slowly crossing at 2. Not like this, but slowly, because there are 3 solutions, x equals 2 there. Any questions? Okay, now I have to determine this maximum. I see that the maximum is between 0 and 2. So second in calc, maximum is 4. From 0, enter. 2, enter. Just give me the maximum. And it says 0.2, comma, 16.8. That's the local maximum. Can I determine the range of this function? Yes, it's not difficult for this one. Look at these arrows, and you will say the range must be right. Right. You're a very good group. Very good. You always answer my questions. I'm very happy. Okay, I want to show you a word problem. So you see where is this applicable? Here it is. That's one of the most important and most fascinating fields that I wanted to enter, but I couldn't. It's a long story. I'll tell you why later. The medical field. So here it is. During a diagnostic evaluation, a 33-year-old woman experienced a panic attack a few minutes after she had been asked to relax her whole body. The graph shows the rapid increase in heart rate during the panic attack. Okay, so let's take a look at the graph for a second, and then I'll read the rest of the questions. Now, look at the graph and say, answer the following question. Can I fit through the points? Forget about the fact that the points are connected. Just look at just the points. Disregard the graph. Just the points. Do you think we can fit a linear function through these points? Of course not, right? Could we fit a quadratic function through these all these points? No. Could we fit a square root function? An absolute value? Nothing that we've studied before works here. Okay, perfect. So, first question. For which time periods during the diagnostic evaluation was the woman's heart rate increasing? Remember, we are not asked from which to which, but the time. Between 1 and 4, the heart rate is increasing, and between 8 and 10. Do you agree with that? Perfect. For which time periods during the diagnostic evaluation was the woman's heart rate decreasing? Between 4 and 8, and between 10 and 12. Excellent. How many turning points do we see in this graph within the 12-minute period? So remember, up, down, up, down. So how many turns? Exactly 3. Up, turn, down. Turn, up, turn, down. 1, 2, 3. By turns, we mean max, min, max. Do we all agree with 3 turns? Knowing that, what is the minimum possible polynomial function that we could fit? You can say degree 10, and I'll have to say maybe. I can say no, but I'm asking for the minimum degree that we could fit. Exactly. Right. So if the degree is 4, we expect 3 turns. If we see 3 turns, we expect degree 4. Is that clear? Perfect. So suppose that the polynomial function is use a number of turning points. Okay. For the model, should the leading coefficient be positive or negative? Negative. Correct. Because turn, turn. So it's coming from negative infinity. Of course, we're not going to talk about that because no one can have a heart rate of negative, right? But for the period between 1 and 12, the polynomial function we can fit, we should fit, will have a negative leading coefficient. Use the graph to estimate the woman's maximum heart rate during the first 12 minutes. Maximum heart rate. When x is 10, the maximum heart rate appears to be roughly. Very good. Use the graph to estimate the woman's minimum heart rate during the first 12 minutes. When x is 8, the minimum is, right. So when we're asked about the minimum, we're asked about the y-axis. When we're asked when, we're asked about the x-axis. Location, altitude, right? So this is a polynomial function. We would have not known how to read this function, how to read the graph, if we hadn't had that experience with polynomial functions degree 4. And there are other examples, of course. Any questions? Yes, please, anything. Because for any even degree, there are two options. X squared or negative x squared. So any even degrees compared to x squared. Any odd degrees compared to x. Is that clear? Any even degree is compared to this or this. If it's coming from below and going back, the leading coefficient must be negative. If it's coming from above and going back, the leading coefficient must be positive. This is positive x squared and this is negative x squared. Better? The degree was 4.
Right.
Because it had 3 turns.
Right, I got that.
Right. So if it has 3 turns, I do this, now it has 5. Right? So if I go back to the graph, so 1, 2, 3 cannot turn again. So these have to go to the negative infinity if I extend them. Because otherwise, if it's positive, then I have to have another turn to go up. So now I'm going to have 5 turns instead of 3. So it must be that this goes this way, which establishes that the function we may be able to fit has to have a negative leading coefficient. Is that better?
Yes.
Perfect. Good. Other questions? Anything else? Okay, so in that case, oh, I brought something for you. It's something that I would like to review. We're not going to finish today. We're not going to do this today, but since I copied it, I wanted to give it to you so you can start working on everything you recognize. Do not work on something you don't recognize. Everything is from your math lab. I copied everything from the problems they were assigned. So I'm hoping that you're going to start working on these problems as soon as possible. Just do what you recognize. Don't worry about the rest. We're going to solve everything else in class. Okay. I would like to, in 3.3, I would just want to refresh your memory on division, long division. So 3.3, division of polynomials. We're only going to look at 2. One of them is not in the book, but I just want to present it to you because I'm sure you've seen this before and it's very simple. A polynomial divided by a monomial, which means one term. We're going to make up an example in a minute. You're not going to see this for somebody that is not in the book, but you may encounter it. And the other one is a polynomial divided by another polynomial, which is long division. I'm sure this is a review for all of you, but I will present everything from scratch. That's okay. So let's say x to the fourth minus 3x squared plus 2x minus 4. And let's say we divide by x squared. And this is the first situation, where the denominator is just one term. Well, all I have to do, because it's one term, which I cannot do in any other situation, is just separate it. How many terms do we have at the top? So I will have 4 fractions. That's the only thing I can do. And simplify each fraction by itself. And you can say this is not a division, and I have to agree. And you could say you're not accomplishing a lot, and then I would have to disagree. Only because there are a lot of applications and a lot of things depend on this and follow. But we're not going to do those. So that's why I just want you to see one simple example. But if you take calculus, you'll see how useful this is. So I'll simplify each fraction by itself. This is x squared. I'll simplify here is minus 3. And I'll simplify 2 over x and minus 4 over x squared. And it's done. There's nothing else I can do. So I simplified dividing by x squared. I simplified divided by x squared. And I simplified divided by 1x. And there is nothing else. And finally, let's look at a long division. On page 392, let's start with 22. Any questions on this? Any questions on that? How to divide a polynomial by one term? If you have 2 terms or more here, you can never do this. This is just one specific situation. So 5x cubed minus 6x squared plus 3x and plus 1. And they say we should divide it by x minus 2. I'm asking myself now 2 questions here. Question number 1, are both in descending order? Is this in descending order and is this in descending order? If they're not, I have to rearrange them. I cannot start the algorithm if they're not in descending order. Are they? Perfect. What is the degree of the top? Yes, the degree of the numerator is 3. We have to see 4 terms in there. Degree 3, degree 2, degree 1, and degree 0. All of them are there. No missing term. If there is a missing term, we have to leave an empty space for that term. But in this case, no missing terms. And I divide by x minus 2. On the side, I'm going to write each question that we ask ourselves. X multiplied by what is 5x cubed? 5 and yes, 5x squared. Remember now, we have to go back and distribute. Redistribute and write below like terms. We have to distribute to both terms. So let's do that. So 5x squared times x is 5x cubed, but we have to subtract. Therefore, we always change the sign before we write under like terms, because we have to subtract. Okay, then 5x squared times negative 2 is negative 10x squared, but now this is written as positive 10x squared. These 2 go away. Perform the operations you see and bring down the next in line. If you are comfortable with a different method, I encourage you to use it. You do not have to switch to mine unless you understand it and you still get twice 10 positive. Very good. So let's stop, because it's a very good question actually. So let's stop for a moment. I'll come back. Let's say 3925, 3,925, let's say, divided by 15. So in 39, I know you can say, take your calculator. Yes, but I'm just explaining. 15 goes into 39 twice, 2 times 15 is 30, but if I write 30 and then I write 69, I'm in trouble. So 2 times 15 is 30, but I have to write the opposite because I subtract. So then I get 9, and then I bring the next in line, and then I'm asking myself 15 into 92 goes 6, right? 6 times 5 is 30, 0 and 3, and then 9, but I have to subtract, but 6 times 15 is not negative 90. So every time I write underneath, I have to change the sign. For the same reason, one more time, let's do this. 5x squared times x is 5x cubed. But for the same reason that 2 times 15 was 30 and I had to change the sign, I have to do the same thing here because I subtract. So then 5x squared times negative 2 is negative 10x squared. I subtract negative 10x squared. That means I have to add 10x squared. So I perform the operations I see, and then I bring the next. I bring down the next in line. So then x times what is 4x squared? X times what is 4x squared? At the top, we do not lie, I like to say, to refresh, to tell my students that at the top, we write what we have to. So I have to write positive and 4x. Do you agree with positive 4x? Yes, but now careful, when we write it underneath, we have to change the sign because we subtract. 4x times x is 4x squared, but now I have to subtract. 4x times negative 2 is negative 8x, but I have to subtract. And I bring down the last in line. Again, we don't lie at the top. So what do I have to write? X times what is 11x? This is when I know this is the last possibility, last question. Degree 2, degree 1, degree 0. And these have the same degree. This must be the last question. So we write positive 11. Perfect. So positive 11. 11 times x, 11x, subtract. 11 times negative 2, negative 22, but positive 22. And we box in the remainder. So let's go back here for a second. This is the quotient plus remainder over the divisor. So let me write the problem one more time.
Can I ask you a quick question?
Yes.
So when we do so I know it's a student level with the remainder.
Yes.
We're gonna box it, not put the R23.
No, because I'm going to show you how to write the answer.
Okay.
In a minute. Yes. So I'll copy the problem one more time. It was 5x cubed minus 6x squared plus 3x plus 1 over x minus 2. And this equals 5x squared plus 4x plus 11. This is the quotient. Plus the remainder, which is 23 divided by x minus 2. 23 is the remainder. And x minus 2 is the divisor.
So when we write it for like the test or whatever you want to write.
Yes, quotient plus remainder over divisor. Do you think we have to look at another?
Yes, please.
Very good. Would you like to look at one that is missing some term? Okay, so let's look at 11. 11 on page 392. 4x to the fourth minus 4x squared plus 6x, everything divided by x minus 4. Descending order, both of them?
Yes.
Any missing term from the top?
Yes.
Yes. Degree what at the top? How many terms do I have to see for the full polynomial? Yes. Degree 4, degree 3 is missing, degree 2, degree 1, and degree 0. Yes. So then we're going to write 4x cubed. We're going to leave some space for x cubed. 4x to the fourth I meant to write. Okay, some space for something cubed, minus 4x squared plus 6x, and at the end, the last term. We are dividing by x minus 4. Can anyone tell us the first term at the top? Yes, 4x cubed. Awesome. Great job. Thank you. 4x cubed times x is indeed 4x to the fourth, but I have to subtract. 4x cubed times negative 4 is negative 16x cubed, but I have to write positive 16x cubed. See, because I did not have a term with x cubed, if I had left an empty space in there, I would have not had room to write it. Because I cannot write x cubed under x squared, because I can't combine them. Is that okay? So these two go away. Now 16x cubed, I bring down the next in line as negative 4x squared. Remember, at the top, we do not lie. So what is at the top then? Plus 16x squared. Great job. 16x squared times x is 16x cubed. But I know if I don't subtract, I can't add. So it has to be the opposite always. 16 times negative 4 is negative 64x squared, but positive 64x squared. So I get 60x squared, and I bring down 6x. Notice that you're not going backwards, right? Degree 3, degree 2. The next one must be degree 1, and the last one, if they both exist, maybe, maybe not. And the last one, degree 0. So what next? Yes, but plus, very good, 60x, positive 60x squared minus 60x squared. Negative 240x, but positive 240x. And then we have 246x, and there is nothing else. I know that this is my last chance, my last question, because the degrees are now the same. Degree 1, degree 1, so this must be a clean cut now. So plus, that's it, 246. So 246 times x is 246x, but now I have to subtract. And then I have negative, which becomes positive now. 4 and 2, 16, 18, and 1, 9. I got 984, correct me if I'm wrong. So then the final form is 4x cubed plus 16x squared plus 60x plus 246 plus 984 divided by x minus 4. And here's a question. What if I have an error? How do I know? So here's the answer. It's a very simple answer, though. So if I tell you that 10 divided by 3 is 3 integers and 1/3, would you believe it? You should never believe anything, right? So just check it out, right? 3 times 3 plus 1 is 10. Agreed?
Yes.
In the same way, I will verify this. X minus 4 multiplied by the whole quotient and plus 984, 3 times 3 plus 1, must equal this. If it does not equal that, everything I've done, I have to erase it and start from scratch. So let's check it. We don't have to, but let's check one of them. Check. I have to show that 4x cubed plus 16x squared plus 60x plus 246, everything multiplied by x minus 4, and plus 984, I have to show that this is 4x to the fourth minus 4x squared plus 6x. If I can't show that, the answer means nothing. It's not the answer.
Yeah, that you can look at your calculator.
There is another way, which is the remainder theorem and the factor theorem. So I debated with myself whether to talk about that or not. I don't think it's needed. It's needed for calculus, but it's not really needed here for what we're trying to do. So I will plug in here positive 4. 4 times 4 to the 4th minus 4 times 4 squared plus 6 times 4. If this answer is the remainder, then the solution is correct. But we don't know that. We haven't talked about these two theorems. So that's fine. That's true. That's true. That's true. But we can't do that. So, okay, so I'm going to multiply x by these these 4 terms. That's easy enough. So 4x to the 4th plus 16x cubed plus 60x squared and plus 246. And now I have to multiply everything by negative 4. So minus 16x cubed minus 64x squared minus 240x and minus I think it's this, and then plus 984. So I have to see that this is true. So the 4x squared, yes. These two go away. The the negative 4x, yes, correct.
You left an x off of the top.
Yeah.
46.
Yeah, I did right here. Thank you very much. Thank you. These two are gone. So, but what happened to my 6x?
Isn't that 246 minus?
Oh, yeah. I'm sorry. And this plus this, that's 240. Oh, no, this was 246. Hold on. I'm rushing here, and that's what happens. So that's correct. That's correct. And now this. That's correct. That's correct. Yeah, I messed up. There's some multiplication here. So 246 times 4. 4 and 2. That's 16. Okay, 18. Yes. 4 times 2 is 9. Okay. So these two cancel out. So it is correct, right? So I get indeed 4x to the 4th minus 4x squared plus 6x. Yeah, everything else good. So now we can verify this as well. I didn't put my calculator, but I can do that. Oh, we already checked it. We don't have to. So this is 4 to the power of 5, the 5th power, and then minus 4 to the 3rd power, and then plus 24. And the answer should be 0. Minus 984, right? So that's the 984 that we were expecting, because that was the remainder. Okay, I think enough of that. Is this clear? Is it clear how we use the long division, not synthetic division. We are not covering synthetic division in this case. Any questions? Do you think we are okay? Do we need another example, or can we move on? We're done with this? Okay, so the last two sections deal with rational functions. This, I would say, this is 3.5. We do not cover 3.4 in this class. 3.5 and 3.6 are the last two sections, rational functions. I would say, in my opinion, that these are the most sophisticated functions in this class. I'm not saying difficult, because you are going to recognize a lot from polynomials, but they require a little bit more attention, I would say. Okay, so of course, we are going to look at two different types. There are three different types that we can look at. However, my department decided to remove the third type from pre-calculus, and then why would we keep it in college algebra? I will show you an example, but I will not test you on it. So I will only ask you to look at 2 different types out of 3. So type 1, no one calls them type 1 and type 2 and type 3. Type 2 and type 3. This I will show an example, but I will not, because the reason why we discussed the long division is for this. And here we are not covering it. So I just want to show you one example when we get to it. So I'm going to give you 2 examples from each type. And we're going to analyze what the differences are, first of all. And then we're going to graph them. So let's say x minus 1 over x plus 2. Here's another example. X squared minus 1 over x squared plus 9. 2 examples of type 1. X divided by x squared minus 1, an example of type 2. F of x, x minus 1 over x squared minus 4. And here's type 3, x cubed plus 2x plus 1 over x squared minus 1. I claim that these are type 1. I claim that these are type 2, and I claim that this is type 3. Let's look carefully and analyze what's happening here. So what do you think? I claim that these 2 are from the same category.
Have 2 terms on top of the bottom.
No. Well, what is the degree of the top?
1,
What is the degree of the bottom? What is the degree of the top?
2.
What is the degree of the bottom? Same degree over same degree. So I'll say degree n, degree n. Same degree over same degree. This is type 1. Let's look at type 2. What would you say about type 2? Higher degree in the, that's it. So degree n and degree greater than n. That's type 2. Everything that has a higher degree in the denominator, it's a rational function, it's type 2. They will all be the same. Remember what I said? All odd degree polynomials are all the same. Minor differences. All even degree polynomials are all the same. Minor differences. Same thing here. Yes,
So
Garrett?
even though we're not getting tested on the third type,
No.
so the third type just would be that the degree is greater in the numerator
Exactly by 1 unit.
by 1.
Yes, exactly by 1 unit. So this is degree n, and this is degree n plus 1. Anything else beyond this, we don't know how to handle. We don't have the tools. Okay? So no matter what they say in the book, anything else beyond this, these 3 types, we have to use the calculator. So what's the point? What do we learn? Just punch in a number and a function and say, wow,
We learned how to use a
look at the
calculator.
graph. That's fantastic. Where does it come from? No. Okay. So, of course, we're asked to graph. And here's the list. Of course, the first one must be at all times what? It starts with D. Always. Always, domain, forever, in all functions. Every time I'm asked to graph a function, my first thought must be the domain. And number 2, yes? X-intercepts. Of course, if, and the multiplicities, if that's the case, plus multiplicities, if that's the case. Number 3, very good. Number 4, something, rational functions don't have degree. So it's a polynomial over a polynomial. So in this case, for the x-intercepts, the y-intercept, so connected to the domain is where f of x is undefined for the x values, where f of x is undefined. There are mainly two possibilities: holding the graph, or not both at the same point. The function can have three holes in the graph, but not at the same point where it has a vertical. We have never talked of, yes, vertical asymptote. That's where the function is undefined. It cannot have whole and vertical asymptote. It either has one or the other. 5. And behavior and horizontal or slant or oblique, slant or oblique asymptote. Not both. A rational function cannot have horizontal and slant. Either has horizontal or slant. To be exact and tell you from the very beginning, only type 3 has slant. Only type 3 has a slant asymptote and not horizontal. 6. Behavior of the function left and right of the VA, vertical asymptote. 7. Max min, if any. 8. Symmetry, if any. 9. Range. It's a long list. It all fits in the table. Once you're done with the table, you know you've finished with everything. So it's just words. Yes, questions? Questions?
You said they took the third